Hello, everybody. My name is Emiliano Cortez, and I'm going to tell you today some of the things on our efforts in order to produce hydrogen by using sunlight sources. As you have heard today along the meeting today, so the main idea of these plasmonic nanoparticles is to gather the energy from a source of light, which can be the sunlight or can be any source of light, and transform that energy into, for example, chemical energy by using these nanoparticles as catalysts of chemical reactions. So we have been centered in different types of reactions and in different aspects of this plasmonic photocatalysis world, and I will show you some of the ideas that we have been working mostly towards hydrogen production by using this concept of plasmonic nanoparticles, but also on the synthesis and the scalability of these nanoparticles towards catalytic properties. So in particular, the hydrogen production reaction, it's a really attractive market because if you can read here, so as for like 2020, so this year, most of the hydrogen, 95% of the hydrogen that we have produced worldwide has been mainly from fossil fuels, right? By steam reforming of natural gas, but partial oxidation of methane or coal gasification. So none of these are like clean routes or green energy routes in order to produce hydrogen, which is a highly valuable chemical, not only for like energy purposes, but also for many other industries. So many chemical industries use hydrogen as one source of energy and also one source of chemical compounds in order to react and produce highly valuable chemical products. So in 2019, the hydrogen market or the hydrogen production around the world was over like 70 million tons of hydrogen. And that turns the hydrogen market into a highly valuable market, which has been estimated around like over 100 billions in 2017. However, if we think we need a lot of hydrogen, it's a really high pressure molecule, I would say, or high pressure chemical, and also a high pressure market for the hydrogen. However, if we think in the conditions that we produce hydrogen nowadays, we will see that it's really costly. So chemical commercial hydrogen, it's mostly produced from refineries, from steam of methane, which is the separation of the hydrogen from the carbon in methane. But for that, we need really high temperatures and really high pressures. So temperatures of around 1,500 Fahrenheit degrees and pressures around like 20 bars as needed for steam reforming. So we need to find new ways of producing hydrogen, not also in a cleaner way, but also in a cheaper way. And the idea of using sunlight as a source of energy in order to produce hydrogen in a much mild condition that we are using nowadays, it has been quite attractive. And a lot of research around the world has been paying attention to this in the last few years. And one of the important things of using these plasmonic nanoparticles in order to get the energy of the sun and then use that in order to produce hydrogen from like different sources. One of the ideas is that these nanoparticles or these catalysts, the synthesis of them, it can be easily scaled up. So we can move into massive production of hydrogen because the catalysts that we use, which are these nanoparticles, they can be produced in millions and liters quite easily in the chem lab, I would say. So here in the first figure, we have like some images of different types of nanoparticles that we have synthesized in my group. So different shapes, different materials, or also combination of shapes and materials in order to produce the most effective way of getting the energy of the sunlight and transform it into chemical energy. So here we see, for example, cubes, we see spheres, we see octahedra, rhomboidecahedra, or we see different types of particles like primers, for example, of these other like more complex hybrid structures. We also see structures that are mostly composed of one metal type, for example, gold or iron, or platinum, but also we have hybrid structures where we combine the properties of two different materials in the nanoscale in order to better get the sunlight energy and transform that into chemical energy. So we can produce these nanoparticles in chemical synthesis, so in liters, literally, like we produce these nanoparticles in a huge amount, in millions and millions of nanoparticles, and each of them are catalysts toward producing hydrogen on the surface of these nanoparticles. So how these plasmonic nanoparticles that uses mostly the energy of the sun as a source of energy, and they work at room temperature and at atmospheric pressure, right? So in really mild conditions, only using the sunlight as a source of energy. So how much hydrogen we can produce compared to other type of nanoparticles that operates under different type of energy conditions. And here in this table, we can see that our plasmonic nanoparticles are not far from other catalysts, which has been recently produced in the lab, and that they work under different type of principles. But the idea of using sunlight as a source of energy and using a catalyst in order to transform that energy and to produce hydrogen, it's not far from the very best catalysts that operate under much harsh conditions. So we are really close to achieve the idea of using sunlight in order to produce hydrogen. Of course, it's still a way to go until we can really get numbers that make this technology possible. But also we have been working on the idea on how to create the best reacting conditions for these nanoparticles in order to produce hydrogen. And in that case, but we need to move towards something more like 2D flow reactors. So reactors in where we can put these nanoparticles and the nanoparticles can react with the light and also transfer that energy to the molecule. So having like a 2D surface of these nanoparticles would be ideal because we will maximize the amount of area exposed to the sunlight, but also exposed to the molecules in order to convert the energy. If we have a bulk flask full of nanoparticles, most of the light will be absorbed by the first layers of the nanoparticles, and none of the light will be seen by the nanoparticles at the end of the flask. So we need something where most of the nanoparticles can see the sun, also can see the molecules and react on the surface. So we have been working on different patterning techniques, which are quite cheap and easy to implement in large scale in order to get the most of these nanoparticles absorbing the energy and translating that energy into the molecules. So now the next steps would be to benchmark these ideas of these reactors with these nanoparticles towards some other methods that we have to produce hydrogen and see if we can get some cleaner and cheap way of producing hydrogen for the future. So thank you very much, and I'm happy to answer your questions.
Good afternoon, my name is Anastasia and I'm a PhD student at King's College London. Today I would like to talk about CO2 reduction reaction using plasmonic metamaterials. As you probably know, global warming is one of the major concerns and challenges that we are facing in this century. Carbon dioxide contributes greatly to the global climate change because it's one of the main greenhouse gases that is present in the atmosphere. In principle, there are three main routes for reducing the amount of CO2. It's direct reduction of CO2 emission, CO2 capture and storage, and CO2 utilization. During the past decade, research activities are moving towards the artificial conversion of CO2 into fuels and valuable chemicals through thermochemical, biological, electrochemical, and photocatalytic methods. In the long term, artificial photosynthesis and photocatalytic conversion of CO2 using solar energy and other catalyst is the most attractive and efficient route for the reduction of CO2. Various catalysts have been investigated in defining active and selective candidates. It's difficult to compare the activities of different photocatalysts reported by different groups, but if we look at their conversion rates and compare with natural photosynthesis, it generally agreed that the photocatalytic performance is much higher. However, to drive CO2 reduction reaction is in an economically feasible way, more effort is required to develop the ideal catalyst, which shows a great efficiency, operating at high current density and low voltage, alongside with high reaction selectivity and chemical stability. Other important factors of a good catalyst are cost, small particle size, and high surface area. The overall goal would be the creation of an artificial carbon cycle, whereby using electricity from solar cells and wind turbines and then electrochemically reducing of carbon dioxide to produce hydrocarbons, and oxygenated organic compounds that can be used as fuels and chemicals. So far, a multitude of different hydrocarbons and oxygenated products have been formed on copper catalyst. Some other advantages of this material are its high natural abundance and low cost. In our project, we developed a fabrication method of copper nanorods that have a high reactive surface area due to their geometry and can be used as an efficient nanocatalyst for plasmon-driven catalytic conversion of carbon dioxide. Our fabrication method is highly controllable and can be easily applied to large surface areas with an added benefit of high uniformity. Furthermore, by changing the dimensions of the catalyst of the copper nanorod material, we can tune the optical properties in the visible region, which is crucial for photocatalyst because 43% of solar energy lies in the visible light region. The photoelectrochemical reduction of CO2 was performed using an electrochemical H cell with the PT counter electrode where the water is oxidized, saturated calomel electrode as reference, and the copper nanorod sample as a working electrode, so our cathode, where carbon dioxide reduction occurs. Both compartments were filled with aqueous potassium carbonate electrolyte solution saturated with CO2 and separated with a membrane so the products made at the cathode side don't diffuse over the anode towards the anode side and become deoxidized. In principle, this reduction process can lead to the formation of carbon monoxide and various hydrocarbon products depending on the applied potential. So first we studied the electrochemical behavior of copper nanorod catalyst. So from our potentiostatic experiments, we showed that cathodic current densities measured at each potential and plotted as a function of time increased in the magnitude with respect to an increasing cathodic potential, as we expected. This remained stable over the reaction time. Then we performed the photoelectrochemical measurements by shining light on the sample under illumination of a red laser and applying a negative potential. We observed an enhancement in the current. This means that the incident light promotes reduction reaction when plasmonic catalysts are used. As expected, for a hot carrier-driven process, the plasmonic photocathode copper nanorods exhibit a linear photocurrent response with respect to incident light power. So the next step now is to quantify and qualify the resultant products and study their catalyst selectivity. So to summarize, I'm presenting a great opportunity for driving photoelectrochemical reaction, such as carbon dioxide reduction reaction at nanoscale, using hot carriers from plasmonic metal nanostructure in the presence of light radiation. Thank you very much for your attention.
Good afternoon, everyone. My name is Niklas Gaskin, and this project is on silicon-compatible infrared photodetection. The targeted technology in this project is sub-bandgap photodetection, or better, silicon-compatible infrared photodetection. Silicon is the most widely used semiconductor today. However, it is inherently limited, or its detection limits are inherently set by the bandgap energy Eg. The sketch here in the center shows the classical mechanism of a p-n heterojunction for photodetection. When a photon hits the diode, carriers are excited from the valence band to the conduction band, creating a potential difference in the current flows. However, as you can see, the incoming light must have at least the energy Eg to overcome the bandgap energy. Especially for silicon, the infrared regime is not accessible. An alternative approach is shown on the right-hand side. When we join a metal with a semiconductor and create the so-called Schottky junction, we are left with a barrier which is smaller than the bandgap energy. Hence, we're left with a potential barrier forming at the interface. This so-called Schottky potential is significantly smaller and can be tuned by the interface composition. Additionally, we can excite hot carriers, or in other words, energetic carriers in the metal, which can easily overcome this barrier. In this project, we investigated different materials and different compositions of those junctions to make an efficient Schottky carrier junction. The applications of such a device are manifold. First of all, the strong points. Obviously, it's silicon compatible and hence it is cheap. The fabrication is fairly facile and it is biocompatible, which is in strong contrast to other materials such as indium gallium arsenide, which is a toxic material but commonly used for infrared photodetection. As shown in our experiment, you can create self-powered photodetectors, which hence do not need a bias and don't need a complicated voltage control or bulky voltage control, depending how compact you want to make your device. You can combine it with refractory alternatives to gold, such as titanium nitride, which is very interesting for plasmonic resonances, which can create very high local heat spots. And additionally, you can basically use different geometries by pattern your metal side. So basically, in this, such detectors can use trenches, gratings, rings, and other resonance structures to enhance the injection efficiency and also the absorption of light. Just to name a few direct applications shown here on the bottom. First, cheap and fast photodetection diode in the infrared. Secondly, integration into silicon chips, which is obviously a very interesting goal, as this is not due to lattice mismatch conditions, is not so easy to accomplish with InGaAs or germanium, but very interesting for next generation optical computing. And another one, maybe more futuristic one, are ingestible sensors. So, for example, sensors which dynamically measure your blood sugar and send information to your smartphone. And these kind of devices are particularly interesting for those because your human tissue, or namely your skin, has a transmission window in the infrared. And additionally, such a sensor would need to be small and ideally self-powered, so not depend on an additionally voltage supply. Finally, I would like to come to the experimental results and the benchmarking. In this project, we could show that we can enhance the injection efficiency of hot carriers into a semiconductor by adding a thin titanium dioxide interlayer. These experimental results here are shown in the measurement on the bottom. Titanium nitride, compared to gold, is known to form a thin titanium dioxide interlayer, and this enhances the injection efficiency of carriers and hence the photocurrent about 1 order of magnitude. This can be used as a platform for various other metals and not just titanium nitride. If we compare our results to the state-of-the-art literature, we can see that we're in a well-competitive regime. Photoresponse is basically the photocurrent here. Please note that if we compare our results to commercially InGaAs or commercially available InGaAs, we require 100 to 1000 enhancement to be commercially viable. However, we're confident that this can be achieved by patterning the metal film and exploiting plasmonic resonances, as shown in another poster in this session, and additionally by tuning the oxygen composition of the titanium dioxide interface film. Thank you very much.
Hello, I'm Killian from King's, and today I will be discussing our work on cavity-enhanced bandgap-free photodetectors. Typical photodetectors require light with energy matching or exceeding the semiconductor bandgap, which considerably limits their spectral range. This is a significant problem for silicon-based detectors, which cannot operate far into the infrared, and hence costly materials are used instead. One solution to this problem is to use a metal-silicon interface, where absorption occurs in the metal itself, generating hot carriers that are subsequently injected into the silicon, giving rise to a photocurrent, as shown by these simple figures. In this context, we have demonstrated a device for enhancing this process by using plasmonic and optical cavity modes, yielding larger photocurrents and also spectrally tuning the detection wavelength, greatly benefiting many applications. The cavity-enhanced bandgap-free device is shown here. An optical cavity is formed by two gold films, one of which contains a grating on a silicon substrate. Optical cavity modes sustained by the device result in the resonant generation of plasmonic modes at the silicon interface via scattering from the grating, and thus significantly increased metal absorption in this region, yielding much greater photocurrent. Crucially, we can also actively control the cavity, such as changing the mirror separation, thus directly modifying the peak photodetection wavelength, allowing it to be tuned for specific applications. This device thus offers a number of immediate benefits. The highly stable photocurrent has been shown to be 5 times greater compared to without the cavity modes. Thus, one of the key advantages is this enhancement over the baseline current, as it offers a straightforward means to augment the performance of a wide range of plasmonic-based photodetectors, ensuring that they become more competitive with established commercial technologies. In addition, the tunable response is narrowband and the detection peak can be electromechanically controlled, as shown here, for wavelength-selective applications, including chemical and biosensing. Other approaches, including all optical methods, can also be readily employed. Another benefit of this device is that it can be utilized not only with gratings, as we have shown here, but also with other nanostructures, including nanoparticles and antennas. The grating structure itself has a small footprint, on the order of 15 by 12 microns, and the cavity is compact, which ensures the device is amenable to on-chip integration for many infrared technologies. In terms of applications, this device will directly benefit many areas involving IR detection, as it offers numerous advantages in terms of photocurrent, footprint, tunability, and compatibility with other components. We can think of the device as a sensor operating in one of two modes. Infrared light can be detected using the cavity, or changes in the cavity can be detected using infrared light. Regarding IR detection, this device can be used for photodetectors operating at telecom wavelengths, e.g. 1.3 to 1.6 microns, and integrated onto a chip. This is immensely valuable for optical communication, removing the need for materials such as InGaAs. Infrared imaging technologies can also benefit, such as for biological imaging, which avails of the IR transparency window. In addition, the device can be used to sense changes in the resonance conditions using IR light, i.e. shift the peak detection wavelength as a result of changes in the environment. For instance, it could operate as a pressure sensor, where altering the film separation directly impacts the current generated. Likewise for sensing refractive index changes within the cavity, allowing for direct electrical readout. In short, this compact, tunable, cavity-based device is a very promising approach for enhancing the performance of a wide range of infrared detectors and sensors.
Hi everyone, my name is Andrea Cassi and I am a postdoc working at the Imperial College with the Rupert Hulton's group. And I'm here to present a technique we have been working on. This technique is about measuring the temperature at the nanoscale. But while we are doing that, the knowledge of the temperature within the nanoscale resolution is critical for a variety of applications, such as medicine, nanoelectronics, biology, and solid-state-based devices. And here I am presenting this technique and its possible applications. What this technique is about? It is about remote sensing the temperature of an object, where the object can be as small as you like, pushing the limit of the temperature measurement down to a few nanometers. With such fine probing, assessing the temperature is just the first step for controlling the temperature as well. This technique is reasonably simple. A source of light, such as a laser beam, heats up an interested area or a particle, which emit back some light for the fluorescence phenomenon. This emitted light carries the information of the temperature of the object which has been emitting it. This technique can resemble the more common Raman thermometry, but it gets few advantages. Neither averaging nor labeling is required, less energy and simpler setup are required as well. Here an example of a photoluminescence spectrum from a gold nanoparticle of 50 nanometers radius. This is the kind of data you look at working with this technique. Through some data analysis, you can retrieve the temperature information, as you can see in this example here. A set of photoluminescence spectrum of a nanoparticle under a set of different illumination power has been converted into the temperature reached from the particle at any given laser power. And there has not been needed nothing more than the photoluminescence information. Nanothermometry finds most of its application in biomedicine, but it's largely used in nanochemistry, optoelectronics, and imaging as well. In biomedical application, the key challenge is to overcome the light absorption from the biological medium. Nanoparticles can be engineered to resonate in one of the biological windows where the cell's walls are transparent. In this way, we can access the temperature information from within the cells and tissues, and even heating up with high precision those particles and the close surrounding as well. Here we can see a few examples from the literature where nanoparticles were deployed to monitor the temperature of within a localized single cell, monitor the metabolic activities through several cells, and even assess the intratumoral temperature as well as photothermal heating when exposed to proper wavelengths. Nanothermometry finds application in other fields though. Measuring the temperature within microfluidic channels is important in application where assessing the temperature with ultra small volumes down to hundreds of picoliters is required. This technique can be used this occasion as well. Solid state devices with nanoelectronics and nanophotonics needs a way to monitor and control the temperature at the nanoscale for performances, optimization, and prevention of failure. Being able to assess and control the temperature at the nanoscale brings massive advantages to the nanoscale chemistry, open the way to direct controlling the catalysis locally. In both cases, this technique we are presenting here can be used to bring these advantages. This technique has already been tested to assess remotely the temperature of nanoparticles of different materials. We can see here an example of a set of gold nanodiscs. On the left, there is a theoretical absorption for gold discs at different radius under different illumination wavelengths. And on the right plot is presented the cumulative results of the relation between temperature and power over several experiments. Each of those dots represents the slope of the relation between temperature and illumination power on a single disk, such as the example in the center. The higher the number, the higher is the temperature reached under the same power. The temperature so evaluated is consistent with theory. And we have been able to directly measure the temperature, and knowing the relation between temperature and illumination power gives us the ability to control it as well. The technique has been proven to be reliable and strong. We want to expand our understanding of it, checking its efficacy over new materials and power ranges, and evaluating the damage threshold of these materials. Most of the temperature techniques nowadays are based on bolometer devices, which have countless advantages, but brings several problems as well. For instance, calibration can be a huge issue, especially if it involves reflective materials and metals. And there is no way to scale those devices to detect temperature variation directly at the nanoscale. A different approach, commonly deployed, uses decorative particles such as organic dyes, quantum dots, or nanodiamonds, working as local probes to extract the temperature information on the nanoscale. This approach works well, but often cannot be used on biological application, and the temperature extract is not directly measured, introducing biases and artifacts. No other techniques but the one presented in this poster allows you to measure directly and remotely the temperature at the nanoscale working on any kind of material. So that's it. Thank you for listening.
Hello everyone. My name is Anton. Welcome to my poster on ultrafast nonlinearity in a novel plasmonic material, nanostructured copper sulfide. While copper sulfide itself is a rather well-known naturally occurring mineral, it has recently gained considerable attention by the plasmonic community after it had been realized it's possible to manufacture copper sulfide in form of single crystal nanoparticles that support a strong and tunable localized surface plasmon resonances in the IR, which makes it a good complementary plasmonic system to conventional noble metals. In addition to that, it holds a number of advantages which makes it particularly desirable from terms of practical applications. For example, it's environmentally stable, it's very cheap, and it's chemically abundant. It can be manufactured by using simple wet chemical synthesis, so additional batches of nanoparticle solutions can be manufactured at very little extra cost. It can be used to cover arbitrary areas of arbitrary substrates, as in this experiment our samples were centimeter-sized glass slides covered with nanoparticle solutions. The goal of this project was to investigate and assess the ultrafast nonlinearity arising from hot carrier excitation and decay. It is well known that interaction of metal surface with the strong and short laser pulses leads to formation of the hot carrier population with a very high temperature exceeding 1000 of Kelvin. This temperature, dubbed electron temperature, shouldn't be confused with the temperature of the crystal lattice. Therefore, even though it exceeds thousands of Kelvin, it doesn't lead to the damage to the material. This hot carrier population then decays within typically few picosecond timescales back to the room temperature. In addition to that, as at the initial stage of the process, the time scale that governs how fast the elevated electron temperature is formed is governed by the non-equilibrium hot carrier decay caused by series of electron-electron collisions. These two time scales, the rise time and the decay time, form a basis of the benchmarking that we are doing for this material. In this respect, what we see is that the non-equilibrium decay and therefore the rise time of our transients, optical transients, is within 20 femtosecond timescale, which is more than an order of magnitude faster than in any typical plasmonic metal, including silver and gold, and comparable to that of graphene. Likewise, for the decay time, the number is 150 femtoseconds, which is again more than an order of magnitude faster with any typical plasmonic metal, and again comparable to graphene. These effects combined let's believe that plasmonic copper sulfide is a promising material in terms of ultra-fast switching or polarization control. In addition to the properties of the bulk material, when material is made in forms of nanoparticles, the non-equilibrium decay can be even accelerated, as is known from the previous research on gold and silver nanoparticles, because of the reduced column screening at the surfaces of the particles. This effect has also been observed in copper sulfide, and it makes the initial rise time of the pump probe transits even faster. Now they are at the order of 14 femtoseconds, which is still an order of magnitude faster than the best values obtained for typical plasmonic noble metals, such as gold and silver, as shown in the table here. Therefore, to sum up, we believe that plasmonic copper sulfide is an interesting and promising material for practical applications in field of all optical switching or ultra-fast polarization control. While as you can see from the last panel, all the commercial solutions for optical switching are still working at best in nanosecond timescale, are still based on electro-optical or acousto-optical devices, microelectromechanical sensors, and so on. there are the whole range of new technologies being developed right now in order to push the speed close into the picosecond and femtosecond time scales. And the field of plasmonic optical switching is one of those fast developing fields, as can be seen from this review over here. Therefore, we believe our plasmonic system, nanostructured copper sulfide, will greatly contribute to that field. We also assume that, as any plasmonic system, copper sulfide may be very useful in terms of sensing applications. Thank you for your attention.